I am Dr. D.K. Tripathi, an assistant professor of physics under the Department of Basic Science and Humanities. In the last class, we have seen that what is energy level, what is energy state, what is the difference between energy level and energy state. We also come to know that what is microstate and how we can define the microstate. What are the uh, characteristics of them? So today we will start with the differences between macrostate and microstate. This means that we want to find out that what is the differences between macrostate and microstate. So if you recall the last class, then we have seen that macrostate depends on the macroscopic properties of the bodies. That means bulk size properties of the system of particles or thermodynamic system. Whereas microstate depends on the microscopic properties of the system of particles. Second thing, what we can say that macroscopic distribution, that is macrostate, is a non-specific distribution, whereas microstate is a specific distribution. Why? Because in the macrostate, identity is not taken care of, whereas in microstate, identity is taken care of. Okay, so you just recall that what we did, we have come to know that these are the macro states 0, 4, 1, 3, 2, 2, 3, 1, 4, 0. So these are the possibilities of distribution of four particles A, B, C, D in two compartments. So here we cannot say that which particle is where, but in the microstate, we have told that which two particles are in which compartment. If you want to realize, which we have seen in the last class, that how two macroscopic distribution can be realized, then we have seen that these are the different distributions. So microscopic distribution, in the microscopic distribution, always the identity is disclosed, and because of that, it is specific one. Now, other thing about the macrostate is that macrostate depends on the extensive properties of the body. That means it depends on the mass dependent properties, whereas microstate depends on the intensive properties of the bodies. Okay, this means that in the macro state, we come to know that how the total mass of the system is distributed among the system of particles, whereas how the total energy is distributed among the constituent particles is disclosed in the microstate. So we conclude that one more thing, that in macrostate, for a single microstate, there will be only one macrostate. How you see? Suppose this macrostate 0, 4, it can be realized in only one number of ways, 0 and ABCD. So for a single macrostate, there will be, whereas this 2, 2, this 2, 2 distribution is realized in 6 number of ways. So what we conclude that for a single macrostate, there may be more than one microstates. Whereas for a single microstate, you just recall about this. This is a single microstate, A, B, C, D. What we can write? A, B are the two particles, so 2. And C, D is the another two particles, so 2, 2, 2. For this, B, D, 2 and AC, 2, 2, 2. That means for a single microstate, there will be single macrostate. But for a single macrostate, there may be more than one microstates. So this is very important point which is to be noted. Now, if we further go ahead, what we will find that let us try to understand these things. That means what we have learned till now about the macrostate and microstate with the help of the numerical examples. Right from the beginning, I am telling you that theory is always confirmed with the help of the numericals. So let us try to have some numerical problems so that we can understand that what is the impact of all these theories, what we have learned. Okay, so as a first illustration, we are taking an example. Consider a two particle system. A system is of two particles. Okay, each of which can exist in three states. Three states are there. How many states are there? Three states are there. Epsilon 1, epsilon 2, epsilon 3. What are the possible, what is the possible states if the particles are bosons and fermions? Now, one and two thing is to be noted. We have not learned about the bosons and fermions till now, but I'm giving you a rough idea so that you can understand the differences between the macrostate and microstate. Later on, we will discuss that what are bosons and fermions. That will be discussed in the next class. Bosons are the particles which follows Bose-Einstein statistics, whereas fermions are the particles which follows the Fermi-Dirac statistics. Okay, so two things about one or two things I will tell you about them. So at first, bosons. Bosons are indistinguishable particle. That means if you're taking a pool of bosons, all may have the same name. So they are similar particles. And one more thing about that, that they do not follow the Pauli's exclusion principle. That means more than one bosons can be kept at one place. Whereas for fermions, they are also indistinguishable particles. Okay, that means if in a pool of particles, all particles may be the same particle. That means all may be electron, all may be proton, like that. And but they follow the Pauli's exclusion principle. That means more than one particle cannot be put in one cell. Now you see two particles are there and three energy states are there, epsilon 1, epsilon 2 and epsilon 3. Now what we will have to do, we will have to arrange these bosons in the first case. Suppose we are taking two bosons. So what will be the name of these two bosons? Suppose we are calling one boson as A, then other may have the same name because they are indistinguishable particle. That means they are alike. So if first particle is A, then second will be certainly A. So we have taken two particles A and A. Now we will have to distribute them in the three different energy states. So how we can put them? What I told you that bosons are not following the Pauli's exclusion principle. So because of that, we can put both of these bosons in the first energy state, that is epsilon 1. So no particle will be left to put in second energy state as well as in the third energy state. Now if you do not put any particle in the first energy level, put both of them in the second energy level, no particle will be left to put in the third energy. Now if you do not put any particle in the first and second energy level, put both of them in the third energy level. Now put one particle, that is A, in the first energy level, put second particle in the second energy level or energy state, and then third will not have any particle to be filled up. Now put first particle in the first energy level, don't put any particle in the second energy level, put third particle in the third energy level. Now don't put any particle in the first energy level, put both of them, put one in the second energy level and the third in the third energy level. So what we conclude, that AA00, this is microstate of distribution of the particles, that which particle is where. Both of these particles are energy state epsilon 1. Here one particle is in the first energy state and second will be in the second energy state. No particle is in the third energy state. So these distributions are showing you specifically that which particle is where and how many particles are, which particle is where, how the total energy of the system is distributed, as this one is saying you, that half of the energy of the system is given to this particle and another half is given to the second particle. Third compartment has no energy or no energy is given to this compartment because there is no particle. So what we conclude that these are the specific distributions. Now let us try to write down the macrostate corresponding to these microstates. So macrostate depends on the number of particles or total volume. Just recall the first class. So you see in the first energy state there are 2 particles, so we have written 2. No particle is in the second energy state, so we have written 0. No particle is in the third energy state there, so we have written 0. So macrostatic distribution is 2, 0, 0. This is saying you that 2 particles, both of the particles are in the first energy state and no particle is given to second and third energy state. So this is giving you the number only. Okay, now you see just here, particle A is in the first energy state, particle A is in the second energy state, no particle is in the third energy state. So it is saying this distribution A0 is saying you that which particle is where. But what macrostate is saying, 1 particle in the first energy state. Which one particle we don't know, as these are bosons, so we can know that the same name will be there, but which one particle is in the first energy state we don't know. Which second one particle is in the second energy state we don't know. So these are the macrostate. So corresponding to these microstates, these are the macrostates. Okay, like that for fermions. For the fermions, they are also indistinguishable particles. So if you are taking one fermion as A, then other will be also A. Now how to put that? Because they are following the Pauli's exclusion principle. So what we will have to do, we will have to put only one particle in one energy state. So you see, this distribution will be replicated. We did that. Particle A is filled in the first energy state, particle A is filled in the second energy state, and no particle will be left to put in the third energy state. So what it will be? 1, 1, 0. This distribution will be 1, 0, 1. This will be 0, 1, 1. So these are the macrostates corresponding to these microstates. So I hope that all of you have understood the actual difference between macrostate and microstate. Now we are going to have a concept of a priori probability. So what is a priori probability? Before going to that, let us try to understand that okay, a priori probability. Let us discuss that at first. You just recall in the last class we have taken an example. What was that example? This example. This example. That 4 particles are to be distributed in 2 compartments. I asked you that what will be the distribution. Then all of you have told that this will be, or all of you will tell probably that the distribution will be 2, 2. That means 2 particles will be filled up in the first compartment and another 2 will be filled up in the second compartment. Why all of you have told about that 2, 2 particles? Why not all these possibilities which I told you? If I ask the same problem to a student of nursery class who knows only counting, he will also tell me that 2 compartments are there and 4 particles are there, then there will be 2, 2. Now what you will say that it will be fulfilling the symmetrical condition that if 2, 2 particles will be there, then equality will be maintained there, and because of this symmetry maintenance, there will be no imbalance in the thermodynamic system. Okay, but let us try to find out that why it can be uttered by anyone that the distribution will be 2, 2. Let us try to find out. Okay, now you see, if anyone is saying that answer 2, 2, what does this mean? This means that this calculation exists in his mind. That is why he is saying a student of nursery class who don't know that what is probability, how is saying that the distribution will be 2, 2. That means this probability exists in his mind. Let us try to realize that. You see this distribution, about these distributions. 0, 4, how you can realize it? Put no particle in the first compartment, put A, B, C, D in the second compartment. So it will be realized in 1 number of ways. This will be realized in 4 number of ways. A, B, C, D, B, A, C, D, like that. This will be realized in 6 number of ways, which we have seen in the last class. This will be also realized in 4 number of ways, and this will be realized in one number of. So have you got the answer? That why you have told that what will be the distribution? As 2-2 distribution will be realized in maximum number of ways. That is why this came in your mind at first. If what we are saying, what we are viewing, what we are doing, that is not without any cause. Certainly there is some cause. So the cause was that this distribution can be realized in maximum number of ways, and that is why it exists in our mind. So the probability which is already existing in our mind before the advent of any event is called as a priori probability. A priori means prior to the advent of the event. If some probability is calculated in our mind, then that is called as a priori probability. So this is because of the a priori probability, we have told that 2-2 distribution will occur. Whereas we have seen that there will be 6 distributions, but their probabilities are less. So probably all of you are having the concept of probability. You have learned about the statistical or mathematical probability. What is statistical or mathematical probability? Statistical or mathematical probability is the chance of occurrence of a particular or favorable event out of the total range. That means out of the total range, what is the probability of commencement of or occurrence of your favorable condition? This you are finding on the basis of mathematics, and that mathematics is called as probability. You have learned many things in 12th standard when probability was taught to you in mathematics, that out of a given range, what will be the number of favorable outcome that you have designated as NE, and what is the total range that you have designated as NS, and then you have calculated the probability. Suppose for an example, if I am asking you that what is the chance of occurrence of any number between 1 and 6 if a dice is thrown. So what you will find, number of ways in which your favorable condition can occur, that will be 1, 2, 3. That means 1 is between 1 and 6, 2 is also between 1 and 6, 3 is also between 1 and 6. So NE will be 1, 2, 3, 4, 5, 6, and total number of favorable outcome, total number of sample space, or total you can say this is wrongly written. Actually this is total number of outcomes. This should not be favorable, so just omit this. This cannot be favorable. Okay, favorable should be on the on the numerator. In the denominator it will be total number of, no, it's good, total number of outcomes. It's good. So what it will be? It will be the number of ways in which the event can be realized, that is NE, that is 6, and number of ways in which the total outcome can be realized, that is NS, that is also 6. So 6 by 6, 1. So if you have got mathematical probability equal to 1, this means the event is sure. What does this mean? That if a dice is thrown, certainly a number between 1 and 6 will occur. But if I am asking you that what is the chance of occurrence of any number less than 1 when a dice is thrown, so NE will be 0, because NE, that means number of ways in which your favorable condition can be realized, is 0, and NS is 6, so 0 by 6, that is 0. So what you will get? You will get probability 0. That means that event cannot be realized. This means this event is impossible. So what we conclude, that statistical or mathematical probability is having least value 0 and maximum value 1. If an event is not sure and also not impossible, so what will be its value? The probability value of this event will be between 0 to 1. That means it may have fractional value. It may have fractional value. So let us, for our example, that we want to find out that what is the chance of occurrence of the macrostate 2 when the 4 particles are thrown to fall into 2 compartments. So number of ways in which 2 can be realized, 2 distribution can be realized is 6. We have seen that. And total number of ways in which the event can be realized, that is, this will be realized in 1 number of ways, this will be realized in 4 number of ways, so 1 plus 4, 5. This will be realized in 6 number of ways, so 1 plus 4 plus 5. This will be realized in 4 number of ways, and this will be realized in 1 number of ways. So total outcome when the 4 particles will be thrown to fall down into these 2 compartments will be 16. Whereas this 2-2 distribution will be realized in 6 number of ways. So what we have got? We have got that NE is equal to how much? NE is equal to 6 and NS is 16. So 6 by 16 will be the statistical probability, which is less than 1. This is less than 1. So we cannot say that the probability of occurrence of 2-2 macrostate will be sure. It will be realized, but its surety is 6 by 16. Now, let us have a concept of thermodynamical probability, because in the thermodynamics, there is thermodynamical probability. What is this? This is somewhat different than the statistical probability, because in the statistical probability, what we have discussed, that statistical probability is the chance of occurrence of a particular event or favorable event out of the given range. But here, thermodynamical probability is defined as the probability of occurrence of a particular event. So you see, what is the difference here? Difference is that it is not calculated out of the given range. What is the chance of occurrence of a particular event? It is calculating only what is the chance of occurrence of a particular event. As in the example, we will try to find out that what is the chance of occurrence of the macrostate 2-2, and this is 6. So thermodynamical probability of chance of occurrence of macrostate 2-2 is 6. This thermodynamical probability is designated by letter W. Now, you will be astonished to hear this, that probability is, the value of probability is 6. Yes. You have not learned that probability value is 6, but that was statistical probability or mathematical probability. Statistical or mathematical probability is having maximum value 1, whereas thermodynamical probability is having least value 1. Why? Because if an event will exist or occur, certainly it will have at least 1 probability. So what we conclude, that thermodynamical probability will have least value 1 and it may have any value. So maximum value cannot be defined. What will be its maximum value? We cannot define. So here the thermodynamical probability is 6. So what we come to know, that it will never be 0. If something will exist, certainly it will be realized at least in 1 number of ways. So it will never be 0. It may be equal to 0 or greater than 0, but never be 0. So this is one of the fundamental difference between thermodynamical probability and statistical probability. Now, let us try to understand it by using an example. So consider 2 identical particles. Each particle can be in one of the 3 possible quantum states, 0, epsilon and 2 epsilon. Find the number of microstates of the system for MB, BE and FD statistics. Now you see, macrostate and microstate we have discussed. So the number of microstates in the Maxwell-Boltzmann statistics, that is on the basis of classical statistics, is given by number of energy states to the power of number of particles, that is G to the power n. So here number of particles is 2 and number of energy states are 3. So the value of G is 3 and the value of n is 2. So 3 square, that is 9. So what we conclude, that the number of microstates in the Maxwell-Boltzmann distribution will be 9. In 9 number of ways, the 2 particles, identical particles, can be arranged. if particles are identical. So these two particles can be arranged in 9 number of ways following the Maxwell-Boltzmann distribution. Now, following the Bose-Einstein distribution, they can be realized, or they can, the thermodynamic probability of their realization will be n plus g minus 1 factorial. That means number of particles, number of energy states minus 1. So same thing. Now, if we'll put all these values, we will find that 6. So it's in 6 number of ways following the Bose-Einstein statistics, the particles can be distributed, or the thermodynamical probability of distribution of two particles in 3 energy states following the Bose-Einstein statistics is 6. Whereas if we follow the Fermi-Dirac statistics, that is the thermodynamical probability of distribution of fermions, this is given by factorial g by factorial n, g minus n factorial. Now, if you put the value of g as factorial 3, the value of n as factorial 2, and 3 minus 2, then it will come out as 3. That means the probability of distribution of fermions, if the particles are fermions, in 3 energy states will be 3. So what we have got? We have not got any value less than 1. 9, 6, and 3. So probably this confirms our theory. Now let us try to understand the differences between statistical and thermodynamical probability. Now you see the least value of statistical probability is 0, and it is having the maximum value 1. Whereas the least value of thermodynamical probability is 1, and it does not have any maximum value. Also, we can say that statistical probability runs from 0 to 1, whereas thermodynamical probability is having the least value 1, but it can have any maximum value, any value greater than 1. Now, statistical probability may have fractional value, whereas thermodynamical probability will may have fractional value, but it will never be less than 1. So this is the most important point about the thermodynamical probability. Now, let us start the statistics. These all are just the basic idea to learn the 3 statistics. So there are 3 statistics. First statistics is called as classical statistics, the statistics which was worked out by Newton, Leibniz, and other classical mechanists. So, the concept was given, or it was conceptualized by Maxwell and Boltzmann. That is why this classical statistics is called as Maxwell-Boltzmann statistics. This Maxwell-Boltzmann statistics uses the concept of classical mechanics, and classical mechanics it does not evolve in a single day. That was you can say that developed by several scientists, starting from the Newton to several mathematicians. So classical statistics or Maxwell-Boltzmann statistics, in short, we call this as MB statistics. Now there are 2 quantum statistics which uses the quantum rules. So these are 2 in number. One is developed by Fermi and Dirac, called as Fermi-Dirac statistics, and other is developed by Bose and Einstein. This is called as Bose-Einstein statistics. So there are 3 statistics: classical or Maxwell-Boltzmann statistics, and Fermi-Dirac statistics, Bose-Einstein statistics. The particles which follows the Maxwell-Boltzmann statistics are called as bosons. The particles which follows the Fermi-Dirac statistics are called as fermions, and the particles which follows the Bose-Einstein statistics are called as bosons. So we will discuss the other assumptions of these 3 statistics in the next class, and these are the references which you must go through to understand the subject better. So, and thank you.